In this video, I show you how to handle many different types of trigonometric integrals that you haven't previously seen. So these trigonometric integrals are just algebraic combinations of these 6 trigonometric functions. That makes this become a very, very large class of problems to pursue. So at the very start, you at least need to know the basic integrals, which is all of these. I'm expecting then that as I go through the rest of the work that you've memorized these. So the primary method to integrate our trigonometric functions is to just rewrite the integral. We're going to use identities or use substitution or integration by parts, with the goal being to rewrite the integral as a sum of other functions plus a bunch of other integrals where the newer integrals are hopefully simpler. Now, many of the integrations I'm about to show you all fall into a kind of a particular pattern. For those patterns, there's techniques. Sadly, though, each of them uses their own specialized integration technique, which means there's quite a bit of memorization involved. And also, today's the day where you really need to know your trig, or you're going to really suffer through the process. The first method I call the save it technique. Basically, it goes like this. I want you to consider integrands only of the form that are products of particular pairs of trig functions: sines and cosines, secants and tangents, cosecants and cotangents. Also, the angle in these functions must be exactly the same. Next, what you do is you try u as one of these trigonometric functions. That will then create a du for it, as if you're about to use substitution. Then rewrite the integral by separating the integrand into two pieces, one being what you have for du and the rest of the integrand. Now look at the rest of the integrand. The other function, not what u is, but the other trig function, if the power on that is positive and even, then this technique will work. If not, stop and try the other substitution. Use now the Pythagorean identity to convert the integral entirely in terms of u. You can then, from here, proceed to go and use u substitution. Let's try this technique once. So let's try u is equal to the sine of x first. That would then mean du will equal to the cosine of x dx. So in the integral, I'll rewrite it so that I will save a single cosine, leaving me a cosine cubed behind in the rest of the integrand, and then I have my cosine of x dx. So this will be my du in the substitution. That would be u. Notice it's the other function I have to worry about. But the power on that, while it's positive, is not even. So this will not work, or at least it's certainly not something we want to pursue. Let's just try it again. So I'll look at the integral of the sine cubed of x times the cosine to the 4th power of x dx. And this time I'll try u is equal to, I'll just try the cosine of x. Then du would then be negative the sine of x dx. So that means then negative du would be the sine of x dx. I'll now rewrite the integral so that I save a sign. That means I have a sine squared of x, a cosine to the 4th power of x, and then I have my sine of x dx. That part's du, or at least negative du. U is cosine, so then I have something for that. Notice then the remaining function is not the cosine, it's the sine, it's the other function. Not what u is, the other function. And the power on that is positive and even. So this technique will work now. All you have to do is now use the Pythagorean theorem in order to go, or Pythagorean identity, to convert the sine squared in terms of cosines. So this is then equal to the integration. That would then be 1 minus the cosine squared of x times the cosine to the 4th power of x times the sine of x dx. I can now use substitution. This would be the integration of 1 minus u squared times u to the 4th, and the sine of x dx is a negative du. I'll put the negative in front, du. That's the new integral. Now from here it's pretty easy. We just distribute the portions to get, in this case, a u to the 6th minus a u to the 4th du. The integration then would become from there, that'd be 1/7 u to the 7th minus 1/5 u to the 5th plus c. That's the answer. Well, I mean, that's the answer in terms of u. I want the answer in terms of x, so I'll remember to replace the u's with the cosine. To get 1/7, 1/7, that's terrible, 1/7 cosine to the 7th power of x minus 1/5 cosine to the 5th power of x plus c. And that's the answer. Now, when I say the answer, remember it's a trigonometric expression. There's many other ways to rewrite that expression. This is just one representation of it. Okay, so let's try it again. This time I'll just choose the right path right away. What if I tried u is equal to the secant of x? Then du would then equal the secant of x, the tangent of x dx. And I'll rewrite the integral so that I take away a secant and a tangent, leaving me a secant squared of x and a tangent squared of x. And in the second half of this product, I'd have secant of x, tangent of x dx. This part is du. That's handled. The secant squared is just u squared. That's handled. Notice it's this guy. It's the other function, not what u represents, but the other trig function that we have to worry about. The power on that is positive and even. So we're good to go. We can go ahead and convert that tangent squared using a Pythagorean identity, because we know tangent squared is really secant squared of x minus 1. And then you have your secant of x and your tangent of x dx. So by our substitutions, this will be then the integral of u squared times u squared minus 1 du. You might notice that in the end, if this technique works, you pretty much get something like a polynomial, and then you can integrate from there. So this will then be the integration of u to the 4th minus u squared du. Integrating each of those pieces is 1/5 u to the 5th minus 1/3 u cubed, and then you have plus c. That's the answer. Well, I mean, that's the answer in terms of u. I wanted the answer in terms of x, so I will replace the u with what it's equivalent to. Get the secant to the 5th power minus 1/3. You have the secant to the 3rd power of x plus c. And that's the answer. Once again, like the previous example, please remember this is a trigonometric expression. There's many other ways to write it. This is just one representation of it. All the different representations will just be off by some constant. Okay, let's try it again. Once again, I will just take the right path right from the very beginning. In this particular integration, notice it's a product or quotient of secants and tangents. So I should try this technique first. I'll try u equal to the tangent of x. Then du would equal to the secant squared of x dx. I'll rewrite the integral to get the secant squared of x all over the square root of tangent of x multiplied to the secant squared of x dx. This is my du, so that's fine. Right here, this guy right here, that's u, so that's fine. It's this one we have to worry about. Notice it's the other trig function, not tangent but secant. I need the power on that remaining piece to be positive and even. It is. So I can finish the problem by just going and using a Pythagorean identity on that secant squared to get, in this case, 1 plus tangent squared of x divided by the square root of the tangent of x times the secant squared of x dx. So using our substitutions, that will then be the integration of 1 plus u squared all over the square root of u times du. And then we can integrate this however else we need. This time we'll have to separate the fraction to write it as u to the negative 1/2 and then plus u to the 3/2 by separating the fraction and simplifying the expressions. That way it becomes a sum or difference of things we can integrate. Each of those is easily integrated. We take the power, we increase it by 1, we multiply by the reciprocal of the power. We take the u, we increase the base by 1, 5/2, and we multiply by the reciprocal of that power. And we add the two results and add our constant integration. That's the answer. You can then go back if you like and just replace the u with our tangent. So that is the tangent of x to the 1/2 power, which you can write as a square root, plus 2/5 the tangent of x to the 5/2 power plus c. And that's the answer to the problem. Again, that is just one way to write it. There are other equivalent ways to do so. After all, if you wanted to, little sidebar, if you wanted to, you could first factor out a 2/5 to not worry about the common factor of 2 with a fraction. You could also factor out a u to the 1/2 power. By doing so, what's left over would then be a 5 plus a u squared. And that would be simpler to actually go and plug in tangent into. So you should have your constant integration here in the back. So what you probably want then is a hard, fast rule. When will this technique work? When should you try it? Well, you can only use it if you recognize the integrand as a product of sines and cosines, secants and tangents, or cosecants and cotangent, either a product or a quotient. Just to make the rule easy to understand, think of them as products, so you have to write them this way, and there's raised to powers. The powers, m and n, can be anything. But if you want this method to work, to have a chance of working, well then in the first case, either m or n must be a positive odd integer. If it isn't, then don't try this. In the other case, either m or n must be a positive integer, but m must be an even integer, or n must be an odd integer. That's really unfortunate that the rules aren't all odd integers, but that is what it is. That's how I realize when this will work and will not. Oh, I have very sad news though. This means then there are so many other integrals to consider, and then after this, there frankly aren't very many good techniques left. But there still are some special cases I can show you. For example, you might have a product of at least non-negative even powers of sine and cosine. In that case, there's something we can notice. The power on sine and cosine both must be non-negative and even, or this, we can't really do this technique on it. Another case is you could have a product of a positive even power of tangent and a positive odd power of secant. In that case, there's something we can try, but it's really not very nice. Also, you have integrals sometimes that have only one trig function, secant only, tangent only, sine only, or cosine only. If the power on those is a positive integer, then there's something that will work. If it's not a positive integer, you can also use the same idea to reduce it to an integral where the power on the secant, tangent, sine, or cosine is somewhere between 0 and 1. And then you could also encounter integrals where the angles are different. Here, we don't really have much we can do except use a whole lot of identities. And there are so many others. So I'm going to look at the first 4 here. After this, sorry, but you're just going to have to use identities and be clever as far as rewriting your integral. So the first one we should tackle then is that one edge case where the power on cosine and sine are both not positive and odd. So one variation is they're still positive, but now they're just non-negative even powers. In that case, the typical method is to use what's called the power reduction identities. That's these. You're going to use these identities over and over and over and over again to constantly replace certain portions of the integral until sooner or later the powers on sine and cosine, at least one of them is odd. Once that happens, you can stop. Now, to show you an example, it's going to be quite long algebraically. So let's look at that simple integral. First, I notice that I can write that as the sine squared squared. But I know that sine squared is 1/2, 1 minus cosine of 2x. I'll just use that right now. I'll use a power reduction identity. Now I'll distribute that particular power, the square, and notice the resulting integral, the integrand, is a sum or difference of things. But notice how the powers all went down by at least a factor of 2. Well, now any portion of that integrand that we can integrate, let's just do it right now. I can find the antiderivative of 1/4 and of 1/2 cosine of 2x. That would be those two right there. 1/4 x minus 1/4 the sine of 2x. Unfortunately, the integral of 1/4 the cosine squared of 2x, we are stuck with the same type of problem. The power on cosine is positive, but even. Well, we'll just use the technique again. We'll just replace the cosine squared of 2x with using the power reduction identity. Now, if you look at the identity, you'll notice it says cosine squared of x, but it's equal to 1/2 1 plus the cosine of 2x. The angle constantly doubles. So while the power goes down, the angle doubles. So that's me going in replacing the cosine squared of 2x with what's equivalent to. I'm just going to multiply that out to make the integrand simple. I then just integrate each of those pieces. And finally, I have a 1/4 x and a 1/8 x. That's obviously 3/8 x. This is the answer. Once again, please note that this is just one way to write the answer. There's lots of other ways that are equivalent to this. They're all just off by a constant. Let's now consider yet another variation. Well, one would be is that there's only one trig function, and it's raised to a positive integer power. If it's not raised to a positive integer power, if it's some other power, you could still use this kind of idea to reduce the particular integral to a new integral where the power on the trig function now is somewhere between usually 0 and 1. So, how to go about doing it? First, you should still consider the save it technique. Because, at least in the case of sines and cosines, if the power on sine or cosine is odd, the technique will still work. If the power on secant is still even or the tangent power is still odd, often actually the technique will still work. Go ahead and just try it. But if that's not true, then you should try either integration by parts or some really clever application of the Pythagorean identities. It's a combination of these two ideas. I'll show you what I mean. So what if you have tangents only? In this case, notice the power on tangent is positive and even, so that save it technique won't work. But what I could do is I will rewrite it so that there is a tangent squared by itself. The entire reason to do so is to immediately replace the tangent squared with what's equivalent to by a Pythagorean identity. In this case, that is a secant squared of x minus 1, and then you have times the tangent squared of x dx. We do this because in this case, the goal is, once you use these Pythagorean identities, is to distribute the product to get now two integrals. One we'll actually be able to integrate, and the other, well, you'll see. This is then equal to the integration of the secant squared of x times the tangent squared of x minus the tangent squared of x dx. And we can then break this up into two integrals. It's the antiderivative of the secant squared of x tangent squared of x dx minus the integral of the tangent squared of x dx. Now consider the first integral. That one we know how to do already. You could just be done by a simple u substitution. If you just pick u is tangent, its derivative is secant squared. So this antiderivative is pretty much automatically, you just take the power on tangent, you increase it by 1, and you multiply by reciprocal of that power. That's that one. The other one, though, you have the antiderivative of the tangent squared of x. So look at the beginning and look at the end. And notice the only thing that's occurred is that the power on tangent went down by 2. So you could use this technique over and over and over and over again to eventually get an integral hopefully you recognize. So let's just do it again. So continuing up here, that would then be 1/3 the tangent cubed of x minus the antiderivative. The tangent squared is really the secant squared of x minus 1 dx. And I can easily integrate each of those. That's 1/3 tangent cubed of x. And then you have minus the antiderivative of secant squared is tangent. And the antiderivative of 1 is x. So I have minus x and then plus c. So my final answer is 1/3 the tangent cubed of x minus the tangent of x plus c. And that's how you would tackle that particular problem. Or actually, any kind of integral where you have tangent to an integer power. That particular method will work. Let's look at two other examples. Again, in each of these cases, you have an integration of a single trig function. But if you have an option, you really should consider the other techniques first. So in this case, to find the antiderivative of cosine cubed of x, notice you can rewrite that as the cosine squared of x times the cosine of x dx, where I'm thinking let's try using u is equal to the sine of x, because then du is the cosine of x dx. So I can see that I saved it here, and while that's not sine, the power on this is positive and even. So I can convert that cosine squared into 1 minus sine squared of x, and then I have times the cosine of x dx. So my substitutions then lead the integration of 1 minus u squared du. And the integral now is easy. That would be u minus 1/3 u cubed plus c. Or the answer, of course, would then be, in terms of sine, that's the sine of x minus 1/3 the sine cubed of x plus c. Notice, though, that the next problem, the integration of the cosine squared, I can't do that. The power on cosine is positive, but it's not odd. So that technique I showed you is not going to work. But instead, the power on it is positive and even, so I can use the power reduction identities. This would then be the same as the integration of, you get 1/2, 1 plus the cosine, I double the angle, dx. So that is then the integration of 1/2 plus 1/2 the cosine of 2x dx. And we can easily integrate each of those. That is 1/2 x, and you have plus a 1/4 sine of 2x plus c. And that's the answer to those problems. Notice you don't have to do what I did in the previous one. I can instead just use the techniques I already know. Okay, so now while that's true though, I did hint that you can use the method of integration by parts to integrate these things. I just have to show you how. So it's a kind of a sneaky thing. It's kind of like the save it technique where you save a certain thing to become your du, and then the v is everything else. So for example here, I'd write this as the integration of, think of it as cosine cubed of x, and then I have the cosine of x dx. So I'll say that u will then be the cosine cubed of x, and dv would then be the cosine of x dx. That means then that du would then be a 3. You'd have a cosine squared of x, and then the derivative of the cosine is a negative sine of x. On the other hand, v would be the antiderivative of the cosine of x dx, and that would just be sine of x. So using these as fuel for integration by parts, this then becomes, I have u times v, so I have cosine cubed of x times v, which is sine of x, and then I subtract, I'd have the integration of v, which is the sine of x, times du. Now since that du has a negative, I'll put this partly in parentheses, a negative 3 cosine squared of x sine of x dx. There we go. I'll just go back now and make this look nice. So this is the same as writing, you have the sine of x, cosine cubed of x. If you want to put the cosine first, you can. After all, c comes before s. Then I have a minus and a minus, that makes a plus. I'd have a integration. I'd have a cosine squared of x. I'd have a sine squared of x, and I have a 3. I'll put the 3 right here, dx. There you go. That's it. That's using parts. Now, granted, look what happened, is that I went from an integral where the powers on cosine was positive and even, and I got a new integral where the powers now are positive and even, and now there's sines and cosines. So you might wonder, well, don't you now have to use the power reduction identities? You had to do that before. Why don't you just do it now? Well, you don't have to. You just have to be a little bit more clever. You can use the identities, in this case, a Pythagorean identity. Let's replace the sine squared with what it's equivalent to. That would then give you sine of x, cosine cubed of x. You'd have plus the integral of 3 times the cosine squared of x. And then here you'd have, well, it's 1 minus the cosine squared of x dx. So rewriting the whole thing, so you see where I'm at. We have the integration of the cosine to the 4th power of x dx. That then equals the sine of x times the cosine cubed of x. You then have plus. That would then be 3 times, multiply the cosine through. So multiply the cosine squared through and the 3 through. You would get 3 times the cosine squared of x. And then you have minus 3 times the cosine to the 4th power of x. And that's dx. Next, take that integral and break it up into 2 pieces. That then gives you equals the sine of x, the cosine cubed of x, plus you'd have 3 times the integral of the cosine squared of x, and then dx. You then have minus 3 times the integral of the cosine to the 4th power of x dx. Now I know, you're now saying, oh my god, I started with 1 integral, now I have 2, and they're both powers of cosine. Well, that's okay actually. Using a trick I showed you before, notice that there's 1 of this integral here, and there happens to be 3 here. Let's just add this particular integral on both sides. That would then mean, since on the left-hand side there's already 1, I'm going to add 3 more. That would be 4 times the integral of the cosine to the 4th power of x dx is therefore equal to the sine of x cosine cubed of x. Then you'd have plus 3 times the integration of the cosine squared of x dx. And if you just divide everything by 4, we get the integral of the cosine to the 4th power of x dx is equal to 1/4 the sine of x, the cosine cubed of x, plus 3/4 the antiderivative of the cosine squared of x dx. And that's the basic technique. That's what works in every case. It's just a matter of saving the right thing and using parts in a clever way. So notice though that I went and had an integral of cosine to the 4th power, and I get it that is equal to some kind of function, this guy right here, plus a multiple of an integral of the same form, but the power on cosine goes down by 2. That's why this only works well if the power on cosine is a positive integer. That way you just constantly reduce it. Eventually, though, you get down to this particular integral, and you need to know how to integrate the cosine squared of x dx. But you know how to do that one. There, finally, we can stop, because we know that that particular integral we can use by power reduction. Notice there's no way around it. You are eventually going to use power reduction on this problem. I just avoided doing it from the beginning, but you have to decide whether you want to do it in general this way or not. It is, unfortunately, the only way really to integrate the secant to a power. But the cosine to a power, we have better techniques, and we tend to use those in that case. So anyway, continuing, this is then 1/4 the sine of x, the cosine cubed of x, plus 3/4. You can then replace the cosine squared with 1/2, 1 plus the cosine of 2x dx. And from here, you've seen me do the problem of this, very similar to this one right here. I welcome you to go finish the integration yourself. So let's look at one more example. Suppose you have a product of a positive even power of tangent with a positive odd power of secant. So that's very, very specific. Unfortunately, there's no quick way to do this. And in fact, we're now getting into the type of integrals where there just are no quick answers. But in this case, there is something we can try. It's just kind of long. And that is convert everything into secants. Everything into secants. Because then when you do so, you will turn the integrand into a sum or difference of integer powers of secant. And then you can integrate each of those separately using a previous technique. So let me show you what I mean. For this particular integral, what I would do is I would write this as the integral of tangent squared. I can convert that into secants. That's really secant squared of x minus 1. Then I have times secant of x dx. That then is the integral of, that's just the secant cubed of x minus the secant of x dx. And then that would then be the integration of the secant cubed of x dx minus the antiderivative of the secant of x dx. And each of these are ones I've done before in class, so I'll just write down the answer. The first integral winds up being 1/2 the secant of x, the tangent of x, minus 1/2 the natural log absolute value of the secant of x plus the tangent of x. Then the second integral, the antiderivative of secant, we also know that is, you then have a plus. Oh, there's a minus there actually, sorry, minus the natural log absolute value of the secant of x plus the tangent of x plus c. So our final answer then would become 1/2 secant of x tangent of x. You'd have minus 3/2 natural log absolute value of secant of x plus tangent of x plus c. That's the answer. And when I say that, there's many other ways to write this also. This is just one way to go about doing so. So it was going to come to this eventually. In any other trigonometric integrals, there just are no easy answers. You're going to need to use identities to rewrite the expressions as sums, or at least in terms of integrals that you have already previously seen, so you can use those techniques on them. You should try, if you're desperate, to multiply and divide by certain trigonometric functions. The result is then often to turn the expression from one type of trigonometric expression to another one. So for example, you can convert secants and tangents to sines and cosines just by rewriting them in some way. You can rewrite cosecants and cotangents in terms of secants and tangents if you want to. Maybe by rewriting the expression, the integral becomes easier. As an example of doing that, let's check out that integral. Now right away, the power on sine and cosine are both positive and odd, but the angles are different, which means that technique I showed you, the save it technique, is not going to work. Instead, we're going to need to use an identity. I have to somehow make this become a sum of functions that can integrate, or I have to use identities to make all the trig functions be the same angle, so I can use my previous techniques. No, here though, I've seen that kind of expression before. In fact, I recall what's called the product to sum identity. It's an identity that you were shown in trig, but you probably wondered why would you want to learn it. It's actually because of this, usually at least. So let's see. To go about using it, it says that the sine of a times the cosine of a b, whatever it is, that is equal to 1/2 the sine of a plus b plus the sine of a minus b. So I'll use that right now. This then becomes the integration of 1/2. You get the sine of, just add the angles, that's 10x. Then you have plus the sine of, just subtract the angles, that would then be 2x dx. And that's the new integral. And that's incredibly easy to do. You just integrate the pieces. That would then become a 1/2 of a negative 1/10 cosine of 10x minus a 1/2 a cosine of 2x plus c. And that's the answer to that problem. Of course, you can simplify that, rewrite it in some way. If you don't like, for example, the half out front, you can just distribute that through. And if you don't like the cosine of 2x, you can use another identity to get rid of it. And if you don't like the cosine of 10x in the problem, you can use an identity to get rid of it. So there's an infinite number of ways to write this answer. But they're all the same, just off by some kind of constant. Now, you may wonder how I did that integration so fast. I just used correction by constants. But just in case, as a side problem, I'll remind you how to do the integration of the sine of 10x. It's just a matter of substitution. You let u equal to 10x, then du would equal to 10 dx, so that dx would then be 1/10 du. This would then become the integration of 1/10 the sine of u du. We know the antiderivative of that. That'd be a negative 1/10 cosine of u plus c. And since we know what u is, that's negative 1/10 the cosine of u, which is 10x plus c. And that's how I got that portion of the answer. And that's how to integrate various different trigonometric integrals. After this, beyond the techniques I just showed you, I'm afraid that you'll just have to use identities and be clever. Remember, the goal is to somehow turn the particular integrand into a sum or difference of constant multiples of functions that you now know how to integrate by using these now more advanced techniques.